Good afternoon. This is David Eastwood, Geotech Engineering and Testing. Welcome to our Residential Foundations program. We're not going to be talking about forensics on this presentation. Just going to be residential foundation design and construction, really. Audience, I think we had, last I checked, we had like 180 people. A lot of engineers, structural engineers, civil engineers, a lot of builders. So we got a lot of a pretty diverse audience here. This is my contact information. My email is d@geotecheng.com. And my phone number is 713-699-4000. Send me an email or call me if you have any questions. We're going to put this on YouTube, so you can go back and watch it. You're not going to learn everything I say here in one, this presentation. There's a lot of information. So it's best to kind of, watch it several times with YouTube. Geotech Engineering and Testing has been around for a long time. We've been around for 39 years in Houston. We work all over Texas, Louisiana, Oklahoma, New Mexico, Arizona. We do geotechnical, environmental materials, and forensic engineering. Failures, foundation problems, slope problems, retaining walls, pavements. We work all over Texas, Louisiana, Oklahoma, New Mexico, Arizona. We have our own rigs, so we do a lot of work for builders and developers. You got to be fast. If you work with these guys, you got to be fast and good. So if you have any questions, please type in your question, I guess, in the either Q&A or chat, and I try to respond right away. Right now, I don't see any questions. We're going to be talking about residential foundations. So somebody sent me these pictures of some of these weird looking residences all over the place. See some of these houses. You can see this one here out there. This is the weirdest one. It's got something that you go up and down, I guess. If you fall in the water, I guess. I don't know how they built this thing. Got a tree house there and houses in the middle of the ocean. I don't know how that works. Going back to our regular houses out there, this is Telfair picture. Back in the old days when they were developing it, it's all developed now. When they do subdivisions, they go out there and a lot of times clear all the trees and vegetation, and then start putting the underground utilities and paving in and the detention, and then you have a detention and you have a subdivision. You got a rec center here, detention ponds and all the houses and underground utilities and tennis courts here. There's a lot of work to develop a subdivision. So when you do a subdivision and when you do a feasibility study on a project, one of the things you have to worry about is a phase 1 environmental site assessment. You got to make sure the property or the lots that you're buying, they don't have any kind of contamination. So you do a phase 1 environmental site assessment, ASTM 1527. So for example, you're buying lots, you got to worry about down the street, this old service station here. It's got these storage tanks that have been in the ground for a long time. They could be leaking. And they got contaminated soils. And if they are located at higher elevation than your subdivision, there's potential for groundwater seepage, the plume going to your subdivision, contaminating it. So you're going to have to worry about if they're up gradient, potential contamination from the the leakage, and the barrels could be leaking. You're going to have oil pipelines and gas pipelines. If you have a leak, your pipe busting can cause a lot of contamination in your project. So if you got a project that you're going to develop here in Leak City, in Texas City, you got these storage tanks, and if these storage tanks are leaking, they can contaminate the soils in here. And of course, if you buy that land, you're responsible for all the cleanup costs. So if you are buying a piece of land next to a landfill, this is a sanitary landfill, and if it rains, it's going to wash out the chemicals and the waste, and they can get into the soil and groundwater system called leachates. And of course, it can have contaminated groundwater and soils, so you need to be aware of that. If you are developing in town, like in the Heights area, Westview, Bel Air, Tanglewood, those area tear downs, as you tear down these structures, you got to worry about asbestos, lead-based paint. So you got to test for all those things, remove all the spoils, can develop in a cemetery. Cleaners, if there are cleaners near your site, you got to worry about them. These cleaners, if they have underground storage tanks, they got chemicals that could be leaking. These solvents are carcinogens, and they can cause cancer. And so you got to watch out development next to cleaners, make sure there's no issues there. If this is your site that you're buying now, by the way, this is a picture in 1936, Pasadena. Start developing it in here, and then you start having service stations here, cleaners here, a car wash, service station here, chemical plant. All these things can cause contamination to your land and potential contamination to your site. This is a site, 1925 in the Heights, with just one house there. 1969, there was a service station here. And then they closed it, went out there and tested soil here, found out that the soils were all contaminated. So they had to dig out a lot of these soils here and bring in structural fill and clean up the area before they go out and build a bunch of houses. This is your site here. The red dots are here where the potential contamination exists. We check about a mile radius on your project for contamination. And so we make sure there's no contamination. We look for oil wells. This is the site. The red stuff is all dots or oil wells near this site. And this is near Kingwood area. So when there's oil wells, there's oil pits. And oil pits are bad. You get a report like this on a phase 1 environmental site assessment. Tells you where the leaky underground storage tanks are. There's 14 of them near this site. Underground storage tanks, there's 12 of them. And they show the distance, like there's one within 1/8 of a mile, one between 1/8 of a mile to 1/4 of a mile. And so we look at all the Superfund sites and other things that can cause contamination, landfills. So in a phase 1 environmental site assessment, you do a site reconnaissance, you check with EPA, TCEQ, Texas Railroad Commissions, look at historical review, interviews, property title review, see who owned it, asbestos testing, lead-based testing. If there are structures on the property, if it's raw land, you don't have to worry about it. And if there's a risk of contamination, you do a phase 2 environmental site assessment. A phase 2 environmental site assessment is done in accordance to ASTM E1903. And, that's if your site's been there and you got all these chemicals out there in the ground, you find out there are chemicals there. So you want to check to see if the soils are actually contaminated. You go out there and drill holes to get soil samples, groundwater samples, and surface water samples, and check for potential contamination. Here's the neighborhood, got a pipe busting, and it causes contamination, damage to the wildlife. You got the wellhead there, and This is a wellhead out there near Cypress Wood area. We did phase 1 on this project. There was no indication of a wellhead, but they were cutting for the streets. We found this. That was not in any database, so we had to go back and do a bunch of borings there to see if there's any contamination. We couldn't find anything. If you got some contamination on your site, one of the techniques you can use is dig out all the contaminated soils, stockpile them, cover them with plastic, so that if it rains, it doesn't leach into the soil and groundwater. You put them in containers like this, cover them, to take them to the landfill site that's appropriate for the waste, and then backfill the area with structural fill in lifts, 100% compaction, 8-inch lifts all the way to the top. Notice I said 100% compaction, not 95%. Anytime you excavate and backfill below 5 feet, you got to compact to 100%, not 95%. So wetlands, as part of any kind of a development, or you buying a piece of property and stuff, you got to look to make sure that track is not in a wetland. Wetland are areas that are inundated and saturated with surface or groundwater, and the frequency and duration sufficient to support, under normal circumstances, things like swamps, marshes, bogs. They're regulated by the U.S. Corps of Engineers. And these are some pictures of wetlands. See, the water used to come over here and drop. There's a lot of wetlands, Harris County, Galveston County, Brazoria County, Montgomery County. This is Galveston there. This is out there in Galveston County here, near League City here. We developed this track in here, but this was a wetland, so we couldn't develop it. It's a map of a wetland that you get. The green stuff is where the wetlands are. So you need to identify them and come up with recommendations of what to do. These are some of the vegetation that grow in a wetland environment. And again, you can see the tree. Water used to be here and down. How do I know if I have jurisdictional water? These waters out there. Jurisdictional delineation are performed on a property to delineate the waters of the U.S. You got to use Clean Water Act 404. And most often a preliminary delineation is done. You submit it to the Corps of Engineers, and hopefully you get through it. Wetland delineations are conducted in accordance to 1987 U.S. Army Corps of Engineers Wetland Delineation Manual. To have wetlands, you should have water, hydric soils, and plants that grow in a wetland environment. So hydric soils, water-loving vegetation, wetland hydrology, saturation for 7 days during the growing season. Subsidence, okay? We drill holes in the ground for our subdivisions and just pull all that water out. Subsidence is lowering of the elevation of the land surface over time, and can have wide consequences depending on the location and occurrence, drainage and flooding. In this area, clay compaction resulting from groundwater withdrawal is the primary issue for subsidence. That's kind of what the land looks like initially. The soils are kind of flocculated. We drill holes and put wells in the ground, pull the water out, changing the pore pressure in soils, make the soil heavier, and the soil starts settling. You get this dispersed structure of the soils. That's long-term after groundwater removal. In Houston area, we have slope from Katy all the way down to Galveston. We got the Chicote Aquifer, it could be 650 feet, 2,000 feet down deep. You go Jasper, can be 2,500, and deeper. You got all these aquifers that are just big bodies of sand. We drill holes in them and pull water out. As we do this, the ground starts dropping, called subsidence. These are some of the aquifers we got that starts from Grimes County all the way down to here, and you can see these, for example, this deep aquifer it goes about 7,000-8,000 feet deep, Frio aquifer, and you can just pull water out of these things. And as you do that, changing the soil pore pressure, and the stuff starts settling and causes the subsidence, which contributes to faulting and flooding. You know, this is Goose Creek out there, 1918 to 1926. 3 feet of subsidence here. There was no water here back in the old days, and then subsided, and the water came in. Here's some of the areas near Kingwood that are saturated and flooded due to subsidence. This is Baytown. The wellhead was here. The soil was here back in the old days. And the subsidence has caused dropping, and they got a void underneath the wellhead. This is Kingwood area, flooding. Brownwood. This is a Brownwood near Baytown, 1944. Oh, and you can see 1953. See, as it subsides, it starts sinking. 1978. 1989. Exxon, I think that from what I heard, Exxon had this land here for some of the executives to build houses. Or subsidence took all the land. 2012. So these areas subside, start having flooding problems. This is 1906 to 1987. You can see parts of Houston area on the east side drop it, which is 9 feet of subsidence. This is not elastic. If you stop taking water out, it's not going to come back. It's done. It's dropped 9 feet. This is a U of H stuff in 2018 that shows, you know, as we grow, like in Montgomery County, there are areas that are dropping half an inch a year in Montgomery County. Oh, subsidence, 1992 to 2000, Jersey Village, 2 inches. 2000 to 2011, Spring area, Woodlands, about 1 inch. Katy area, about 1 inch. And as the population grows, in like Fort Wayne County is going to grow by 2050 by 74%. Harris County, 17%. Liberty County, 93%. So as these counties become more populated, they want more water. And as they take more water, the ground is going to subside. This is kind of a predicted subsidence between 2010 and 2050. And you can see parts of Harris County and Galveston County and Fort Wayne County. This area is going to drop 1.5 foot. This area here going to drop, you know, Brazoria County about 0.5 foot. So you can see the predicted subsidence. And of course, you can see the Montgomery County here. It's going to drop about 0.5 foot. South side, the Woodlands area, all the way Kingwood and Splendora. All those areas that are experiencing a lot of growth, they're going to have subsidence and they're going to drop. And of course, that causes flooding and faulting. But we have these water authorities out there that we're going to nowadays. And these water authorities, they use surface water, so we're not going to have subsidence. These are like North Harris County Water Authority, West Houston Water Authority, North Fort Bend, San Jacinto Water Authority, Coastal Water Authority. All these guys using surface water, so we don't have subsidence. This is ADEX extensiometer that shows the ADEX area dropping roughly 0.5 inch a year between 1973 to 1988. This is Pasadena. They're going to surface water. They start subsiding, but they're stabilizing. Faulting. If parts of this Houston area that are dropping, and there are other parts that are not dropping due to subsidence, there are cracks in the ground that have been there for a long time. They become activated. They call them geologic faults. And you can see these faults in here. They could be underneath the buildings. They can extend a couple 100 feet deep. So cracks. There are about 450 faults in the Houston area, all the way from Corpus Christi, Beaumont, Houston. They extend all the way about 100 miles inland from the coast. So you can have all the way to Huntsville, you know, you have potential, you know, faulting. They move average rate of about 0.5 inch per year. This is a geologic fault that you can see there. So you want to develop a subdivision, you got to check for faulting. This is called shear zone. This is the down thrown section of the fault. It's the upthrown section of the faults. You can see the upthrown, downthrown. This is the shear zone right there. Fault going out there and cracking that house. Here's another fault here, cracking this house. That's out there near Carlton Woods, out there in the woodlands. There are faults in the woodlands area. You see the lineation here, going in there, cracking the paving here, going towards this structure. This is a bump out there on the road. You can see that bump in the road out there, north of Galleria on Post Oak. There's a fault going up here. This is the upthrown section. This is the downthrown section of the fault. See it again, downthrown section, upthrown section of the fault. Fault's got two components, the upthrown section, the area that's high, the area that's dropping, downthrown section. These are soil layers that kind of go out of whack. It's a clay, comes over here as it drops. This is sand. This is a fault scarp. And so to check to see if there's a fault, phase 2, you can do borings in here. And based on changing the elevations in the soil layers, you do geophysical testing and you figure out where the actual fault line is. And you can see the fault line here from aerial photos. Of course, that's one of the areas you look at. This is the downthrown section. It's the upthrown section. The downthrown section is darker, so because there's more water there. Okay. And you see the lineation here on an aerial photo. That's the fault. Downthrown section, upthrown section. There's more water in the downthrown section, so it's greener. In a flooding situation, this is the fault. Downthrown section, upthrown section. If your site is wooded, it's very hard to find you got a fault there. Or it's got tall grass. It makes it very hard to find out if there's a fault there. So if you got sites with tall grass or trees, you can try LiDAR, uses a laser light to pick it up, the change in elevation. You shoot it from like an airplane or helicopter or something, and at the time it takes to hit the ground and come back, you can calculate the change in elevations. And pick up a LiDAR fault like that, change in elevation. It's this track in here, you got a fault going right through it, picking up through the LiDAR. The site is wooded, tall grass. You hydro-axe it, remove the trees and tall grass. You don't change the elevation of the site. You just hydro-axe it and remove all the vegetation. And you go back and look at the change in elevation to see if there's a fault there. There are faults in Dallas, San Antonio, Austin. They're not active, so we don't have to worry about them. The soils across these faults are different, though. Sometimes one side is clay, the other side is sand. So if you're building in a fault in Austin, near a fault, make sure you do a detailed geotechnical to make sure you got the right soils. And you can see the Houston Gulf Coast area, the Beaumont. There's a lot of faults in here. You can see the fault maps that we got. The fault maps that we have don't show all the faults. There are a lot of faults that we don't show because property owners do not want us to disclose them. So, but there are some public knowledge faults there. And this is another fault map. So you can see the tick marks. It's the downthrown section. This is the upthrown section of a long point fault on I-10. Okay, so you get a lot of faults out there near Pearland, for example. We had a client wanted to buy a piece of property in Pearland. And it's near the salt dome in here, McCullough. And you can see all the faults in the area. And when we look at this is the land in red, and there was a fault going right through the middle of it. The green is like a pipeline. We developed the hazard zone, about 130 feet wide. The downthrown section was like 80, 90 feet, and the upthrown section was like 40 feet. The reason the downthrown is wider on the hazard map is because hazard zone is because the downward movement, the down thrown section moves more. You can turn this area here to a linear detention or a linear park, but you cannot build houses there. This is a school out there in Pearland, next to a fault out there near Pearland Parkway. We didn't recommend them to build it, but they did. They put them on deep piers, anchor bolts, and beams, and they had to go back and adjust it every once in a while if the building foundation moved due to faulting. So when we get calls on geotechnical exploration for residential developments, we do borings with our rigs. These are rigs. We have like 10 rigs. This goes about 120 feet. This goes about 20 feet. These other ones go about 30 feet deep. This goes 120. These are little ATVs we got. The site looks like this, nice and dry. We use our truck mounted rig. It goes out there and drill. If you got a lift station or a water plant or something like that, we use our bigger rig. They got to go deeper borings. If your site is wet, we use our buggy rigs. These buggy rigs can go out there when there's a really soft, marshy areas. Cost more money. If the site is wooded, like in the woodlands area, you got to do a path to clear the area. And you clear a path and you send the rig back there. You do the borings next to the biggest tree on the property. You want to get root fibers from the trees. That tells us about foundation design. Root systems extend to an area there is oxygen and water. When there's no oxygen and water, they die. That defines our active zone depth. Active zone depth is the depth at which the soils from that depth all the way to the top are subject to movement due to changes in soil moisture and climatic changes. So we do the borings next to trees and get root fibers. These are portable rigs. It was about 20 feet deep. We pulled the portable rig behind our ATV. The subdivision lots are wet. We do the borings like that with a portable rig. Can go down about 20 foot deep. Most of our sampling is done with Shelby tubes. These are 3-inch diameter hollow tubes. You hydraulically push them into the ground and get soil samples. This is a soil sample that we extrude. That's how the soil sample looks like. You cut the ends, you put them in foil, put them in plastic, put them in a wax box. You look for, I guess back to here, you want to keep the moisture constant on that soil. If the soil dries up, you're not going to get good results. So you're going to have to test the soils usually within 2 weeks so that you have fresh soils and proper test results. You look for root fibers. As we get deeper, the root fibers become smaller. Root fibers extend all the way to the areas to define the active zone depth. That tells you the zone at which soil changes in moisture and is subject to movement. It's not an expansive soils area. If the soil is non-expansive, it doesn't matter. So it's only important if your soils are expansive. We do sampling in the sand, the split spoon sampler. We get 140 pound hammer, you drop it 30 inches. And we get samples of the sand because we cannot push Shelby tube into the sand because sands are too dense. We bend the tube, we cannot get a sample. So we drive it into the ground 6 inch, 6 inch, 6 inch, 18 inches. And we get the blow counts. This is a split spoon sampler. It splits open, so you open it up and you look at it. That's a sand sample there. If your blow counts between 0 and 4, they got very loose sand. Loose sand between 5 and 10. Medium dense 11 to 30. Dense 31 to 50, and very dense over 50. Most of our soils in the Houston area are very loose to loose. So when we do foundations like a post tension slab, we design them for a very loose to loose condition to be able to, for bearing capacity purposes. If you start going deeper, you're going to hit rock. In general, rock in Houston is about 2,500 feet deep. So we don't have to worry about it. But if you go out there near Conroe, 105 area, go out there west past April Sound, you're going to hit some sandstone. You go out there on Alaska, near Lake Livingston, you hit sandstone. You go to Huntsville, you can hit some sandstone. Of course, you go to Dallas, San Antonio, Austin. You have Austin chalk in Austin, limestone. Dallas, Fort Worth, you got shale and limestone. So same with Austin. Groundwater, when you leave a job site, you got to measure the water level. Most of our borings, you know, they're so fast, you cannot really measure water levels. And to truly measure the water levels, you got to put what's called piezometers in the holes to measure water levels over a long term. The way you measure the water level, you get a tape measure with a weight at the end of it, you throw it into the ground, and when it goes plump, you measure the water. That's how you measure the water level. You also have perched water table in the areas, parts of Houston, where you have sandy soils over clay. Basically, water, when it rains, just sits on top of the clay because it cannot permeate it. And so the sands get all saturated, and water just sits here, and called perched water table. Just sits out there like a bathtub. Yeah, and you can see it like within a couple of feet of the surface. But right there, so it's called perched water table. It's not groundwater table, it's perched water table. Like that. Number of borings. If you got a custom home, for example, you got to tear it down first. You got a lot like this, like in West.GE, you got a 50 by 100, you got a couple of borings, 20 to 25 foot deep. You know, I mean, braze height to go 25 foot. You know, West.GE, I like to do 25. Do the borings next to the biggest trees. These are the reds, the boring locations. Green is where the trees are. You do the borings next to the biggest trees to get root fibers. It could be an existing house that you're going to demolish. You can do the borings, you know, next to the trees. That's not important to do the borings right underneath the house. That's not a very important issue. Preliminary, and we get a lot of development where you want to buy the land. They got 100 acres, for example. They want to know what kind of soils they have before they buy it. It's very important to know what kind of soils you have, because you need to identify the soils, what's called PVR, potential vertical rise for that site. It's not economical to build on sites with PVR greater than 4.5 inches. So you do one boring every 10 acres and get the borings out there, and find out what kind of soils you have all the way down to 20 feet. If you got lots that they have, you know, you're going to buy, you got to do the borings for these lots. The spacing should not exceed 200 feet by the Post-Conditioning Institute, PTI. They got to be at least 15 feet deep. Usually you have multiple builders in a subdivision, so we do what's called a split and do the borings for both builders or all three of them, and save a bunch of money for these guys when they do splits. These are the borings again for the lots. They should not be more than 200 feet spacing. Some builders like to do them at 200 foot spacing. Some builders are more conservative. They want to do it at 100 foot spacing. And some builders don't want to do it in every lot, just to make sure they got the right soils, because soils vary. So we use the truck man or rig to get out there and do the borings. Do laboratory testing. We take the soil samples, bring in the lab. One of the tests we do in the lab is called liquid limit test. This test, we take soil in a cup like this. You add water to it. When it becomes liquid, you grab it and put it in a cup like this, kind of groove through it with this. Turn this handle 20 to 30 times. When the groove comes together after shaking and banging, you take that sample of the soil, you put it in a cup like this, you get the wet weight of it. Want to know how much it weighs when it's wet. Then you put it in the oven and dry it up, and you get the dry weight of it. Difference with the wet weight and the dry weight is how much water is in the soil for it to behave liquid. And then we want to know what the plastic limit of the soil is, and what moisture the soils behave plastic. You do a plastic limit test. You roll it to 1/8 of an inch, and you get the wet weight of it. You put it in the oven and get the dry weight of it. And then we know how much water is in the soil for it to behave semi-plastic. The difference between liquid and plastic limit is called plasticity index, PI. If your plasticity index is less than 20, you got low soil potential. 20 and 30, you got moderately expansive. 30 and 40 has got highly expansive. About 40 is very high soil expansive. A couple other tests we do in the lab. Hand penetrometer and toe range to measure strength. Estimate the bearing capacity for your foundations. If you use a slab-on-grade or you use piers and all that, you got to know what the soil strength is. So in a hand penetrometer test, you take that and push it to the end of the soil sample. You read what kind of a strength it has. In a toe range test, you put it at the end of the sample. It shows you the intorsion and read what kind of a strength it has. We'll also do unconfined compression tests. In this test, you put a sample in here and you've got a proving ring, deflection. You shear the soil to see how much load it can carry. So it's called unconfined compression test. Soil types in Houston area and in Texas. We have a lot of black clays, brown clays. This is a clay site right here. We have sandy sites. That's like in Galveston area and the Woodlands and the Katy. The sandy sites and the silty sites. The grain size of the silt is bigger than clay, smaller than sand. It's really hard material to build on. And so they got silty sites. So we got clay, you go deeper, you get orange clay, you go deeper, you go white clay. Then you get weathered rock. And you got rock below that. Fill. When we do houses, foundations and stuff, on these subdivisions, we do mass grading. That means they dig out the detention pond and storm sewer, sanitary line, all that fill goes on the lots. So all that fill should be compacted 95% of standard product density. You can build on top of the fill. All these houses on subdivisions, most of them are built on top of fill. And as long as the soil doesn't have organics and it's properly compacted, you can build a house on it. There's a thing called 79G letter. You get that from a testing lab, and shows all the compaction for all the lifts, and if everything passes, then you can build a house on it. But you got to make sure you got compaction results for all the lifts. Engineering analysis. So we got the expansive soils, the orange stuff, all over Texas and Louisiana. The soils in Texas are variable. So you need a soil test every time we do a subdivision or you're building a house, a custom house. These are the soils that can expand up to 1,500% in Texas. In the U.S. That's by the U.S. Corps of Engineers. So we have a lot of expansive soils in the U.S. Texas and Louisiana, the expansive soils. See the expansive soils, they develop shrinkage cracks. The cities like Houston, Dallas, San Antonio, Austin, they all have expansive soils in them. So places like Lubbock and El Paso, they got, caliche and sandy, silty soils. So we have expansive soils that's got more problems with foundations. So if you go around Houston, starting near where I live, kind of near Roman Forest, Splendora area, we got really sandy, silty soils out of here. You go to Kingwood, you got fat clays, gumbo, you got trees. You get close to Lake Houston, you got really sandy soils. You go out there in Crosby, Dayton, Mobile, Baytown, LaPorte, Pasadena, Pearland, Seabrook, Lake City, Dickinson, Missouri City, Sugarland, New Territory, Pecan Grove, Rosenberg. All these places, you got highly expansive soils. And there's a lot of potential for movements. You go out here to Cinco Ranch, the soils become sandy. We've got perch water table problems, pumping. You go to Katy, Bridgeland, Fairfield. You got sandy soils, pumping problems, and perch water table. Tomball, you got some areas got fat clay, some areas sandy soils. You got the woodlands area, you got real sandy soils. Some areas, you got a little bit of expansive soils. Start moving out there south of Conroe, real sandy. North of Conroe, real fat clay. So Conroe's got weird soils. All these places such as Brazoria County, all that, they got all fat clay out here. A lot of expansive soils with PBR, some areas of greater than 4.5. You go inside Houston, you do custom homes. West U, Bel Air, out there, Missouri City. Tanglewood, you got highly expansive soils, oak trees, a bunch of attorneys. So make sure you do the foundations right. Potential vertical rise. That's a concept that you need to be aware of. PVR is what tells you how much heave you can expect on a site. So if there's a lot of movement on your soils, you're going to have a certain type of foundations so that you're not going to have movement. Because if you have too much movement, you're going to have all kinds of cracking in your walls, sheetrocks, and all that, and the brick. So you don't want to have a lot of movement. This is a map I developed for Houston. It shows PVRs, like Kingwood, you can have 3 to 4 inches. Cosby areas, well, Bellevue, 5-6 inches. Baytown, 5-6 inches. You go all the way down here. Fresno out there, Missouri City, 5 inches. Sugarland, 5 inches. Greatwood, 6-7 inches. Rosenberg, 5-6 inches. Fulcher, 2 to 4 inches. You go to Katy area, 1.5 or less. Bridgeland, go on 1.5 or less. You go to 290, anywhere from 1 to 4 inches. Fairview, 2 to 3 inches. South of Condo, 1. Woodlands area, 1 to 4 inches. Just depending where you are. You go West U, Bel Air, Tanglewood, 5-6 inches. So this kind of tells you the kind of potential movement you can have on your projects. PVR for most buildings on piers should limit it to 1 inch. Okay, if you use piers, you got PVR should not exceed 1 inch. If you're using a conventional reinforced slab, a post-tension slab, you can have PVRs as high as 4.5. So most builders, if they do PVRs greater than 4.5, they do things to get it down to 4.5. Some builders, they have a limit of 3.5. So just depending on the builder, this value can change. Some of the things you can do to reduce the PVR is, of course, you reduce changes in moisture by placing sprinkler systems all around the whole structure. Don't put sprinkler system just on one side, just the front area. So if you do that, the front just get wet and move up and down, but the sides and the back don't move. So you get differential movements and get cracking. The deeper your exterior beams, the more stable change moisture is underneath your slab, the less movement you're going to get. So, make the beams deeper. When you have a driveway, put a space between the driveway and the house so that you have uniform moisture like this. This is not acceptable. Don't put the paving against the exterior beams. You got planter area here, you got wet. This area is dry, this area moves. You're going to get differential moisture and cracking. Positive drainage, you need to have 5% drainage away from a house, exterior beam. Your exterior concrete should extend 6 to 8 inches above the top of the topsoil. So don't bring your topsoil all the way to the brick line. There's got to be 6 to 8 inches of space here. So make sure that's there. When they build the houses, the pad should be, structural fill. Do not use sand or silt to build your pads. Sand and silt transmits water, and if you got expansive soils underneath it cause a lot of foundation problem and perch water table. So do not use sand and silt to build pads. Remove all the grass, of course, when you build the pad. If you want to have a PBR of 1 inch, you got a site with P.I of 60 and movement active zone of 10 feet. You got to move as much as 7 foot of soil to get your PVR to about 1 inch. That's very uneconomical. So what you do, of course, for a post-tension slab, you can have PVRs up to 4.5. You don't have to move anything. No removal. If you got piers, then yeah, remove that thing, the soil, go with select fill on top, or you do basically crawl space or structural slab with void boxes. This is select fill that we use on projects. Select fill is a soil with liquid limit less than 40 PI between 12 and 20. Minimum 50% should pass number 200 sieve. If you have expansive soils, you're going to get a lot of cracks in the soils. During the summertime, especially, these cracks get filled up with debris during the summertime. Then you get a big rain. The soils wants to expand, expansive soils. Doesn't have any place to go. It starts cracking at 45-degree angle. It's called slicking sides. So if you go out there and dig a pool, the whole side of the pool is going to cave in. That's because of the weak plane of the slicking sides. Or if you have drill piers, the bale is going to cave in because of the slicking sides. So because of that, if you have a bale, you make them 2 to 1, or you may have to go a straight shaft if you got slicking sides out there. Slicking sides also define the depth of active zone, not movement active zone, but active zone. We've seen, slicking sides all the way to the depth of 25 feet in Houston. So that shows a deep active zone in some areas. But your movement active zone is only 10 feet. So although your active zone can be deeper, but your movement, that area that moves, is only 10 feet. These are pictures of slicking sides. So if you look at the geologic map, north of Buffalo Bayou, you got sandy soils, Lacey Formation. South of Buffalo Bayou, you got Beaumont Fat Clay Formation. So we have fat clay. It's a boring log, by the way. It shows all the soils data. You got fat clay. Below that, this fill. Below that, you got fat clay again, natural soil. P off 39, 35. Below that, you got sand. You hit the water at about 13 feet and moves up to about 9 feet because of hydrostatic pressure. And so in this case here, you got to use piers on your foundation. If you do, you have to put them 18, 20 feet, 22 feet deep. So you got to use the slurry method of construction. So if you put them shallow, you're within the active zone depth, the movement active zone, and then your pier is going to move up and down. This is a soil stratigraphy. So if you got a subdivision, we do the lot borings. And you can say that the top 18 feet from elevation 30 to elevation 18, top 12 feet, it's all clay. Below that, you got sand. Below that, you got clay. So if you got to use the pier foundations, if these soils are expansive, you got to go through the sands and put the bales right here, which means that you got to use the slurry method of construction, make it more expensive. If your soils are non-expansive, you can put the piers directly on top of the sands. The type of foundation we use for residential structures in Texas are deep foundations such as drill piers, piling, auger cast piles, helical piles, press piling, or you can do a slab-on-grade conventional reinforced slab, post-tension slab. You can use spread footings. You can use mats. Foundations at risk. If you do a residential foundation, the best one, of course, is a structural slab with piers. That's what we do in Westview, Bel Air, kind of use crawl space. And or you can use void boxes. The expansive soils heave up and doesn't move the slab. That's because of the voids. Slab on fill on piers. Back in the old days, we used to do a lot of slab on fill on piers. But now, because of the Atlas 14 and potential flooding, we use crawl space. But you can use select fill underneath your slab and reduce the PVR and put the piers underneath it. You determine the fill thickness based on the soil PI and the PVR. You can do a stiffened slab, floating, what we call super slab. Floating stiffened slab on piers.
You design a whole slab on piers and stiffen it. It can move up, but it cannot go down because it's got piers there. Then you can have super slab that doesn't care about compaction of the soil underneath it, as long as you dig the beams into the natural soils and go with like 6 or 7 inch slab between the grade beams. Doesn't require compaction. If you want to go fast and don't worry about the earthwork, you can use a super slab. 95% of all the houses in Houston are designed on conventional reinforced slab or post-tension slab, mostly post-tension slab. These are floating foundation system. They perform fine as long as they're designed and constructed properly. And if the ground moves, they move. So if you're building a $2 million house, I would use a structural slab with piers. If you're building a $500,000 house, I would be using a post-tension slab. Drill piers. This is an auger rig, and this is the bell rig. We go drill holes in the ground, put the pier in the ground. This is a kind of a custom home. This is where the pier is going to go. Drill a hole with an auger. You drill it. Oh, then you got a reamer. Usually for residential, it's 36 inches in diameter. That's the bell. You open it up 36 inches. You put it in the ground. You make sure you measure the bell size. Sometimes these guys cheat and put a 24-inch DL bells on it. You don't want that. You got to make sure the hole is vertical. You measure the depth. If your design depth is 18 feet, make sure it's at least 18 feet deep. A lot of these guys cheat on the depth and the size of the piers. Use a bell tool. You put it in the ground and sweep it. Make sure you got the right size bell. These are 36-inch diameter bell. You got to have the bell tool for 36-inch diameter bell. Make sure there's no water in the bottom of the hole. You can have up to 2 inches of water. You can pump the water out. Then you put your steel cage in. Like that, and start pouring concrete. Make sure the concrete doesn't hit the sides. So you pour your concrete. You got your steel there. Yeah, don't bend the steel. Oh, this is your bell. The steel comes all the way up. You won't bend the steel into the grade beams. You sleeve it with plastic so that it can go up and down if you have expansive soils. This is the pier. This is the steel. You sleeve it. That's your beam steel. And allow the beam go up and down. It's the bell, steel, void boxes, your slab. Your void boxes extend between piers underneath the floor slabs. You got to put void boxes underneath the grade beams as well as the floor slabs, not just underneath the grade beams or not just underneath the floor slabs. It's got to be at both locations. It's a typical makeup. You got interior beams, you got the pier locations. Then there's the beam depth, the pier detail. The way you determine pier depth is kind of scientific. Some people, they just go out there and put them in. They have no idea how, how to put the pier depth in. There's a concept called moisture active zone. That's how you determine whether root fibers, slicking sides. That's the zone at which soil experiences change in moisture. Then there's a zero movement line or movement active zone. That's be equal to smaller than moisture active zone. Like in Houston, it's about 10 feet. Dallas, San Antonio, and Austin is about 15 feet. And then for piers, you got anchor zone. The pier got to be deep enough to resist upward movement from the soils above the zero movement line, and to resist uplifting the pier, pulling the pier out of the ground, and lifting the house. The way you determine the active zone depth is if you hit a sand layer, if you hit a rock layer, if you got 2 foot below the lowest root fiber that you measure, when you get a change in suction of the soils less than 0.27 pf, when your liquidity index in the soils become vertical, depth of slicking sides, and if you know the depth of historical water table, which is hard to do. If you have trees, your active zone depth is going to be deeper. Because trees suck so much moisture, so your active zone is going to be deeper, but not the movement active zone. The active zone is going to be deeper. Moisture active zone is going to be deeper. So when you design a pier, you got to design it for downward movement. You got end-bearing skin friction. You can't count on the skin friction within the zero movement line or movement active zone because the soil opens and closes and moves. So that's what you count on when you design the piers, or downward movement. But the most thing that controls the design is upward movement. For these lightly loaded structures for foundation for residences, the soils above the zero movement line will grab the pier and start pulling it up. You have to anchor it below that to resist upward movement. You can't count on the bell to resist uplift because by the time the bell mobilizes, you have moved already 2 to 3 inches, you already have sheetrock cracks and doors sticking. So you cannot count on the bell. So knowing your movement active zone, the rule of thumb is twice the depth of the, you double up your movement active zone for your anchor zone. So if your active zone depth is 10 feet, your pier's got to be 20 feet. So that's kind of give you an idea what you're looking at. Piers in West University, Tanglewood, Braes Heights, Mireland area should be at least 18 to 20, 25 foot deep. In Houston, your estimated active zone, movement active zone is 6 to 10 feet. The pier's got to be at least 12 to 20 feet. Dallas, estimated movement active zone is at least 15 feet. So your piers are 25, 35 foot. San Antonio, 15. Austin, San Antonio, the same depth. So if I've got a house in West U, I got this big tree here. I got a PI of 50. My active zone, movement active zone is 10 feet. My movement active zone is 10 feet. My pier's got to be at least, 18, 20 foot deep here to resist uplift. Here's another house in West U. You got your sand in here, so your active zone is 10 feet, the movement active zone. You put the piers in sand all the way down. Since the skin friction on sand is less than clays, you got to put it deeper, so your piers may be 22, 23 feet deep. And of course, you've got to use a slurry method of construction, which triples the cost of your piers. Of course, in this case, you can use what's called helical piles to design your foundation system. In the floor slab areas, if your soils are expansive, use a structural slab with void, such as crawl space, or you can use a slab on structural fill. You can do lime stabilization of on-site soils. You lime stabilize all the fat clays, get the PI down, and you can use them as select fill. You can do a chemical injection, put the slab there. And of course, your soils are non-expansive. You just compact that soil and you put your slab directly on top of it. Structural slab, Atlas 14, we got the flooding issues that we got. A lot of the houses, in the West U, Bel Air areas and Tanglewood, you got to be above the floodplain elevation. So a lot of the builders are using crawl space for their foundations. They go out there and, of course, build a crawl space. This is the garage. Build houses. It's crawl space areas. Got to make sure you got positive drainage in the crawl space. No low areas, no trash. You got to have vents in it for the air to get underneath it. So this is another top crawl space in here. You can see the precast panels here on top of the beams. Structural slab system. This is another house out here, and this is in Friendswood. It's supposed to be a structural slab system on piers. The house had all kinds of foundation problems. Yeah, put it on steel beams out for foundations, piers. But the structural engineer cheated on the pier depths. He put it only at 10 feet. The geotech report said put it at 18 feet. He disregarded the geotech report and put it in 10 feet. So the piers were within an active zone depth. The expansive soil grabbed the piers and lift them up. But highly expansive soils and the trees were removed when they built this thing. So the area was very dry. So all the piers came out of the ground. Had all kinds of foundation problems. These are some of the trial pictures during the construction. There's another house in Braze Heights. A couple of attorneys lived here. And highly expansive soils. Put the piers at 10 feet. They had a right foundation. They had structural slab. They put in void. They didn't put void boxes underneath the grade beams. Piers were only 10 feet deep. This is the crawl space. The expansive soils grabbed the piers and pushed them up. Since there was no void boxes underneath the beams, all the beams got lifted up too. So they had a lot of cracks in the house. Here's another house out there in the Seabrook. They didn't even do a geotech on this site. They put the piers at 8 feet, really expansive soils. The house started moving. They put these spread footings out here underneath the foundation to level it, but they put it right directly on top of soil. Well, they start settling and heaving up and down. The house started moving again, so we told them to go in, remove all this stuff, and put helical piles in. So all that's had to be removed because that shallow foundation system, essentially the foundation for the house was a floating slab, so it was subject to movements. Shim it like that above these blocks that they put underneath the beams. Structural slab on void boxes. You put some of these houses on void boxes, on piers. The void boxes should be in the grade beams as well as in the floor slabs. You put 2 layers of steel in here, Matt. You pour the concrete. These are void boxes. When they get wet, they deteriorate and create a void underneath the grade beams and the floor slabs. So expansive soils will lift them up. It doesn't lift the slab up. You dig the beams. You put your void boxes in. You put them in the beams as well as in the floor slab areas. Then you put a storm cover on it. When you put the steel in here, it doesn't punch the void boxes. It's a 5 millimeter thick waterproof sheet bubble extruded polyurethane board that can be used over void boxes in lieu of corrugated paper. Designed to protect the top of the void boxes from puncture caused by pinpoint loading like steel placement. So that you put them on, and you put your vapor barrier on top of it. And you put your steel there. Here's what we'll call a 2-way slab. You use a structural slab like this. Essentially, you don't need any beams, just a 7-inch concrete slab on piers. And you drill your piers first. You do your plumbing. There's no beams, so you don't even have to compact that soil very much, as long as it can support the weight of the void boxes and the concrete on top of it. Then you put your piers in, you put your steel in. It's called thickened slab around each. It's got drop caps. Put the steel in. Those are your piers. These are temperature steel here. These are post-tension cables. Usually this slab is 6 to 7 inches thick. You pour it, got a structural slab on piers. If your soils are expansive, you put void boxes underneath it. There's a 2-way slab, structural slab system that you may want to use in your custom homes. Not for track homes. Dallas area, they use what's called terra firma type foundation systems. I don't know how much they use it nowadays, but they drill a hole in the ground just like you do when they put the piers in. You ream it with a bell. These are the piers. You put post-tension slab on top of it. You put something called a peck on top of the piers, puck on top of the piers. That's the puck right there. Post-tension cables. You got the chairs in here, plumbing. You pour your slab. You find your puck. You remove it. You put a screw in there, like that. You screw that screw into the puck. You turn it like this with these handles. And as you do that, it lifts the slab up. And then move the slab becomes a structural slab. Here's they move it by 6 inches. They say it's not very expensive to do it this way, but I don't know. And you fill that with polyurethane material, the hole. Then you go out there and grade around it. Structural slab-on-grade beams. In the heights area, if your soils are non-expansive, you put your exterior beams in. And then you go in there, put beams on, wood beams out there in between. There's no piers here, okay? You only use this if you have non-expansive soils. And then you go out there and build a house on it. These are typically type of system used. Non-expansive soils, the crawl space. Kind of a pier and beam type stuff, they call it. So, structural slab on post-tension slab. A lot of builders do this. This is a good foundation, cheap. Do a regular post-tension slab and you put walls around it for crawl space. So you got a regular post-tension slab, you got your cables, you got your beams, and you start putting walls around it. That's a crawl space. You got a PT slab underneath it. If you're doing a crawl space, you got to make sure you got positive drainage everywhere. You can't have water just standing underneath your crawl space. Water gets underneath there and gets into the piers, and you're going to have movements. So you're going to have positive drainage, no trash, no nails. None of this is acceptable. Helical ponds are great foundations. You can use them. If you have sandy soil, shallow water tables, instead of piers, when you're using a slurry method of construction, they're cheaper than piers. If you're using a slurry method of construction, they're more expensive than piers. If you're using dry method of construction, you just drill them in the hole in the ground. These are helixes. You just screw them in there. You got a bracket. You put your grade beams on top of that. Here's a site. These are helical piers. They're building this house in here with helical piers. They run them down to about 30 feet on this job. You just screw them into the ground real quick. You can do it all in one day. It just doesn't matter if you got sand, clay, and stuff. You drill them in there. You get your design capacity, and you stop. You just screw them in there. These are helical plates. On the bigger projects, you got bigger plates. You use them a lot for industrial projects. You drill them into the grade beams. In areas you need to use lateral loading, you do a 12-inch hole in the top 10 feet. Fill it up with concrete to give it more surface area to resist lateral loading. Or you can put them at batter to resist lateral load. You put them in the grade beams. Oh, I don't know what I did. You put them in the grade beams, 6 to 8 foot spacing. If you need to put void boxes in, you put your void boxes in. With chairs for your concrete. Conventional reinforcement slab, they're great foundations. They're floating slab systems. That means the ground moves, your slab moves. Got interior beams. Usually anywhere between 8 to 15 foot spacing, depending on the PI of the soils and what the PVR is, what your design parameters are. Usually we see a lot of them in places like in the country area where, there's no post-tension slab type deal. You put number 3 bars at 15 foot inch spacing, typical. You got a makeup. You put the interior beams in there. Make sure all your grate beams are clean. Put your plumbing. Put your vapor barrier in. Put your steel in. Chairs underneath the steel. You put concrete. You finish it. Vibrate that concrete. Rolled wire mesh steel. We don't recommend the use of any rolled wire mesh steel in your slab. It ends up in the bottom because there's no chair. So we don't recommend use a rolled wire mesh. Don't use it. Ends up in the bottom. This is not acceptable to lift the steel like that. You should have chairs. This is not acceptable. The steel ends up in the bottom. So you have no temperature steel in there. This is not acceptable. These idiots, they're pouring concrete. You got, a vapor barrier here. Below that, you got steel. So the concrete is not going into steel. So they have to jackhammer the whole thing up and do it over again. Post-tension slab foundations, you got interior beams, exterior beams. Beam spacing are usually about 8 to 15 foot spacing. You got cables going through the grade beams. Sometimes one, sometimes you go double cable. You got a certain drape. You got a waffle slab system. You put your steel cable in. You got chairs underneath the cables. This is your live end. You pull the cables to put compression in the post-tension slab. This is your dead end. That's your anchoring system. It's a dead end, live end, dead end. It's a dead end here. You pull the cable here, put compression in the slab. Initially, you put like 33 kips of the load in your cables. This is your interior beams. Make sure your vapor barrier is in contact with your grade beam. Do not let it float. Got to have chairs underneath. This is not acceptable. There should not be any void underneath the vapor barrier and the bottom of the grade beams. You pour the concrete, your maximum concrete slump should be 5 inches. Pump in the concrete. Start finishing it. That's what the slab looks like. Remove the forms after you pour the concrete within 24 hours. You're going to start stressing it. Usually you have to have concrete at least 22,000 PSI concrete strength. Usually about 3 to 7 days. This is a jack. You pull it up with the machine like that. Minimum concrete strength 2,000 PSI. Elongations excessing to 10% should be reported to design engineer. So Depending on the length of your cable, man, I don't know what I did here. Okay, so I got to go back. So depending on the length of your cable, you should have a certain amount of elongation. If you're supposed to have elongation of 5 inches and you get 6 inches or 7 inches, there's a problem with that cable. You got to talk to your structural engineer, find out what's going on, why you have so much elongation. Because you're supposed to put 33 kips in your cable in compression when you pull these cables. Your string should be 2,000 PSI. Elongation is greater than 10%. Should be reported to the design engineer. Tendons in excess of 100 foot should be stressed from both ends. So you have to stress them for both ends of the cables, like you do in an apartment complex. You mark the cables with paint. You measure it when you pull it. So that's your elongation. So you measure the elongation. Oh, got to make sure your jack is calibrated. Cable blowouts. You got some pictures of the bad concrete. You're pulling in here. It was too early. You got to blow out. You got to go in and repair all that. You can see the anchor here. Initially, when you have a slab, initially when you pour it, you have no compression in your slab and no tension in your cables. You go out there and put 33 kips initially in your cables. That puts your concrete in compression. With time, it drops to about 28.9 kips, called wedge seating. And final condition, with time, it drops to 26.5 kips. So your slab is in compression. It reduces the need for steel. You can carry more moment and shear. Then you go out there and cut the cables, grout the pockets. You got to be clean, free of any dirt, oil, grease. Bonding agent can be used to enhance the bonding between the grout and the concrete. All the dirt needs to come out, sand and stuff. The stressing pocket should be filled with non-shrink, non-metallic grout as soon as possible. Tendons after the stressing. On the north circumstance, the grout pocket should be left exposed. We don't want it to rust. You cover it, and then you go out there, use the grout and fill it with. Do not use non-shrink grouts that they got chloride in them. Anything that's bad for the steel, you cover it up. Design. We got a lot of engineers here, so I'm going to talk about design a little bit. You do slab design from a soil standpoint. There's a concept called Thornton-White Moisture Index. It basically is based on average over 20 to 30 years of rainfall in excess or deficit of average evaporation rates. So negative TMI means sustained moisture deficit. You got a lot of evaporation. Positive TMI means excess moisture. There's a lot, like Houston, generally it's got the positive TMI. Right now we're in a drought condition, but generally Houston soils are moist. So if you look at the TMI table of Texas, Houston is plus 18. That means you got positive moisture. Dallas is 0. That means the evaporation is equals to actual moisture retention. San Antonio is minus 15. Honest is minus 15. That means, every time it rains, everything evaporates. You got a moisture deficit in those cities. So in terms of the expansive soils, you can see this bands of expansive soils in Texas. The soils more than 50% area with high swell potential. These are clays with no swell potential right here. These soils, they got moderately. The blue areas got moderately expansive soils. Times of climatic conditions, that kind of controls how much movement you're going to get. Climate controls a lot of stuff on your foundations. for post-tension slabs or otherwise. Texas, you got the brown, yellow, green, and blue kind of a color. The brown and yellow, you know, you got TMIs between 20 to minus to 40. That's positive. That means you got excess moisture in these areas. A lot of trees, extra moisture, 0 to 20. A lot of moisture. The green area is minus 20, 0 to minus 20. You got essentially moisture deficit. In dark blue, you got a lot of, you know, kind of like a drought conditions. A lot of the moisture deficit. So if you got a slab that you're going to build it in areas the climatic is kind of wet, you got a positive TMI, the brown area. If you get a drought, the edge of the slab is going to drop. You get edge drop. In the green area and blue area, you got moisture deficits. So if you got a big rainfall, the edge of the slab going to heave up. You're going to get edge lift on these slabs in terms of movement. So climatic kind of tells you how much, what kind of shapes your slab is going to have, what kind of movements you're going to have. When we design slabs in places with extreme temperature, extreme dry or wet conditions, we call it post-construction. Climates dry to extreme wet. Those are the TMI between minus 15 to plus 15. Places such as Dallas, San Antonio, and Austin. You design it for post-construction. They got extreme dry to wet condition weather. Places like Houston, we usually are always wet. Or there are places that minus 15, they're always dry. So they don't have changes in moisture in climatic conditions very much. So if you got a post-equilibrium condition, like in Houston condition, we have a post-equilibrium condition in Houston. So the moisture usually wet. The movement values, even for a PI of 62, is only 1.8 to 2 inches. That means you're going to be able to design a slab, 30-inch slab, 32-inch slab over there with grade beams. Oh, it's not very bad. It's not that bad. Bearing capacity. Residential foundations do not fail in bearing usually because the slab itself supports as bearing the grade beams. Essentially, your net area with bearing for slab is 16 times the slab thickness at the interior grade beams and 6 times the slab thickness at the exterior beams. So if your slab is 4 inches, 6 times that is 24 inches for the exterior beams. In other words, if your beams are 12 inches in the exterior, you add 24 inches to it, you got an area of 36 inch for bearing. That's a lot of bearing. In the interior is 16 times the slab thickness. So that's 16 times 4. So that's what? Whatever that is, that's like 64 inches plus the bearing area of the grade beams, 12 inches or 10 inches. So you got 74 inches bearing areas. So you put load on it, it spreads the load. So a lot of times what we say is, if somebody said your slab failed in bearing, a lot of these slabs don't fail in bearing, post-tension slabs or conventional reinforced slabs. So this is your interior beam. The zone of the influence is 16T, 16 times the slab thickness. And in the edge, in the beam areas, 6 times the slab thickness. So, affected trees. Trees affect foundations, residential foundations, and commercial foundations. Trees can cause a lot of foundation movements. When you go out there and cut trees and build houses, the soils are so dry because the trees have been sucking the moisture out, so the ground is dry. And you measure it by a concept called soil suction. Soil suction is just describe ability of a unsaturated soils to attract or retain moisture, water, in terms of pressure. A typical Houston area, when your soils are dry, you got a soil suction of 4.5. As you go deeper, you get to equilibrium suction of roughly about 3.5. And then if your soils are wet, you got near the surface, you got a suction of about real wet soils, 3.0. As you go deeper, you get to equilibrium suction of about 3.0. Basically, if you're don't have a tree and your soils are basically wet, if the soil dries up, you usually dry up from a wet condition to equilibrium suction, just to climate. But if you cut a tree, your soils are very dry. Your actual the depth of dry suction envelope is 4.5 all the way down to the depth of 10 feet. And so for the soil to get the moisture and starts heaving up, it moves all the way from a dry condition of 4.5 to about 3.0. That causes a lot of heat. So when you take a tree out, you got it from a dry moisture condition, suction profile, all the way down to a wet condition. And that's really a post-construction type of condition where you got a lot of movements when you take a tree out. So if you look at your design values for a soil with PI of 40, your Y/M values, if you don't have trees, it's 1.4, 1.6. Your PVR is 2.6 inches with PVR of 40. Okay. Now, if you take the tree out right off the 0 year, right after you take the tree out, your edge lift is going to move to 5.3 inches. So that's going to make your slabs very expensive. You can't build it. It's greater than 4.5. The PVR is 2.6 inches of steel. With time, after 1 year, you drop to 2.5 to 1.6 inches because the soils start hydrate. Usually after 2 years, you can design them as 1.4, 1.6, like the tree's not there. Sometimes it takes 5 years or more to get there. I'm just trying to show you the concept. Here's another kind with a PI of 62 soil, PVR 4.5. Your Y/M values for edge lift is 1.8. Edge drop is 2.0. You take the tree out. Right after you take the tree out, your edge lift goes to 9.3. And after 2 years, after 1 year here, you drop to 1.8. These are the conditions you have to use chemical injection. Basically, if you got soils with PVRs of greater than 4.5, or areas you got, to remove the trees and stuff, you got clay platelets, they got negative charge, you got water, you got positive charge. The clay wants to absorb the water, expands the double layer clay, soils starts expanding. And so what we do is we do a cation exchange. In this case, we do chemical injection. We remove the non-valent cations like sodium and potassium and replace them with divalent cations like calcium. So when you put the calcium in here, the negative charge reduces and it doesn't absorb as much water. It's called cation exchange. You got these chemicals, you mix them in with water, then you inject them into the soil. This is Sienna Plantation. We injected a bunch of lots there. This is near Bayswood area. This is the hole where we did the chemical injection. The soils where usual chemical injections are good are highly expansive soils with PVRs of greater than 4.5, where you have a lot of shrinkage cracks so that the chemicals can disperse. If your cracks are small, there's going to be less dispersion of soils, chemicals. After you do chemical injection, edge lift drops to 1.4 inches. Center lift or edge drops to 1.6 inches. So your PVR drops to 1.2 inches. So most builders, this is a soil with PI of 62. If they got a PVR of 4.5 or 6 or 5, they do chemical injection to get it down to PVR of less than 4.5. When you do chemical injection, your PVR usually drops it a lot. Waffle type slab. This is the concept that they use in Dallas on a lot of the multifamily type projects. They go out there and essentially scrape the grass, compact that soils, and with a vapor barrier there, put these plastic boxes, put your steel cables in there, set the forms. These are your grade beams. If you got plumbing, you take one of the boxes out. For concrete, that's your slab. You don't have to dig any beams or anything. It's pretty fast. You stretch your cables, then you kind of grade it. If you want to have a moisture barrier around the slab before you build it, usually you can just kind of get one of these blades and put in the vapor barrier in the ground, usually a 15 mil, or you can use a ditch witch. Usually about 3-4 foot deep. That reduces the moisture going under the slab, and you can save money on your slab design. Because essentially you got 36-inch or 48-inch beams. So your PTI value is going to be smaller. I heard numbers like $5,000 per slab to put them in. If you're doing a beach house, use a timber pile systems or other types of piles. You have to drive them into the ground. These are round or square. They got to be treated. These are 12 by 12, 10 by 10. And you just drive them with a hammer into the ground. Don't use a backhoe to push them in. Oh, you cut the top if you need to. We don't want them to be cracked up. That's not acceptable. You can also use fiberglass piles. You can put concrete inside of them. Build bitch houses. Fiberglass filled up with concrete. You can drive it in. You can vibrate them in. If you got a big structure in Galveston, you can use pre-stressed concrete piles. You just drive them into the ground. Great areas, big areas. It's kind of a third world country. They're driving piles there. Yeah, use TechStop Spec 404 for pile driving. You get a refusal when you have more than 120 blows per foot. And you can do pile holes if you cannot drive the piles. You can do jetting. Do a pile of holes and make a hole and just drive your piles in the ground. You can do jetting. That's a 2.5-inch diameter pipe, 150 psi water pressure. And you make a hole, you drive your piles. You drive it at least 1 foot below the tip elevation. Kind of TechStop gives you the hammer sizes when you drive these piles. If you're doing a beach house, use timber pile. Your stroke on the on your ram got to be at least 5 to 10 foot, and the energy for the hammer about 330 times R. which R is the design load in tons. So you got a 20-ton pile, that'd be 330 times 20. These are some pictures of distressed beach houses. Unfortunately, a lot of the beach houses in Texas are not engineered. They just go out there and drive some piles in there, 10, 15 foot deep, and then they get a hurricane, and they lose the beach house. They get scour. So that's still going on. All these beach houses are going in, not engineered. And that's a sad situation for the owners who don't know what's going on. So a lot of cracking. Good construction practices for post-tension slabs. Adequately brace your forms. Check the form layout. Make sure that it's correct, level, and square. This is not acceptable. Look at this thing here. All the cables are in the water. Poor drainage around that slab. A lot of trash. Look at the cables. These are all bad construction practices. Foundation makeup after rain. This is the house out there in the Mineland area. You put the piers in. You put the slab in. It rained. And that's what it looked like. So they had to go out there and fix it all up. So it's very important to do a proper geotechnical work and structural work when you do residential foundations or commercial foundations. So if it's your original cost of the construction is this is when you get sued, change order. And so it's very important to have proper design. Unfortunately, a lot of the clients, what we see, they try to cut corners on their design and construction. And some of the design parameters that are wrong. Not proper testing is done on your soils. And so that's why we see a lot of foundation problems. So you got to do the job right. It doesn't cost very much money to do designs on these things and construction, and so that we don't have trouble later. Any questions for this segment? Okay, I'm going to quickly go through another segment here, quality control and testing. Back in the old days, Romans used to build roads. These are the workers. And these guys were checking the construction. If you cheated on your concrete, they speared you. If your density failed, they poked you with a spear. When you build your lots, move all the grass and weeds, all the foundation, establish good drainage, compacted subgrade soils to 95% standard product density. If your soils are wet, you can aerate them, you can fly ash them, you can lime them, remove and replace it with the dry soils. In small areas, you put lime in there, that soaks all the water out. When we build stuff, we have to go out there and remove all the grass and weeds and trees. All the roots greater than half an inch should come out. When you take out that tree root, this whole area got to be demucked. All the water needs to be removed. All the soft soil got to be removed. Backfilled with unside soils or structural fill. You 8-inch lift, got to run density tests. Make sure it's good. Otherwise, the side of your house is going to settle where you took that tree out. This is a lot out there. You can see the tree was removed, cut the trees, but you can see all the roots all over the place. You cannot just shove soil into the hole where the tree was removed. You got to put it in lifts and compact it. Otherwise, your slab is going to settle. All these roots got to come out. When you build your pad, you cannot put all these roots out there in your pad. We had a hell of a problem for this project here. The contractor was leaving all these roots out there in the pad. That's not acceptable. All the roots needs to come out. You even left the tree trunk in there. All the roots come out. If you bring in fill, the fill should not have organics in it. No grass. You cannot have trash in your fill. No brick, no concrete chunks. None of that in your fill. You cannot build your pad with this kind of stuff. This is not acceptable, all the rock and debris. Perched water table, as we discussed before, parts of Houston area, we have these sandy soils over clays. When it rains, water just sits in the sands and it starts pumping. This is your regular groundwater table. It's perched water table. When you got a perched water table, you got sandy soils. You take out those trees and grass. The area starts pumping. You can't build houses here. Water just sits there. You see the lots here. You take the trees out. You got water just sitting there. And you set your forms. You dig your beams. It gets filled up with water because of perched water table. It's a pumping soil, perched water table. So we have a lot of perched water table in areas such as Katy, out there in the Woodlands area, 290, 249 area, all the way up. We have a lot of perched water table. You get a truck out there, it gets stuck. If you got sites that got perched water table, you scarify, open up to dry, you improve drainage, you can do soil mixing, you can do chemical modification of soils, you can do removal and replacement. If you have a drought condition, you can go out there and open it up and let it dry, and the sands won't pump anymore. But usually we get a lot of rain, so that may not be a very good option. Drainage, if you got these sandy soils over clay, you put these bleeder ditches there. You take them all to a detention pond, about 3 foot wide, 2 foot deep. You drain all the sand and silts. You put them in a grid. You go to a detention pond and pump it into a neighbor's property. You can mix the on-site soils with clays and, the on-site sand and silts with clays. So if you dig your detention pond and you find a bunch of clays, or your channel, you find a bunch of clays, you take them to the site, you dump it on the sand and silts, you grade it, and then of course you disc them in. You mix it 60-40, 40% sand, 60% clay. You pulverize it too. Then you compact it. It doesn't pump anymore. You can do chemical stabilization. You use lime or fly ash or cement. This is dry hydrated lime. This is quicklime. You add a bunch of quicklime to the sandy soils, and or fly ash. And he dries it up. This is fly ash. Do not use lime slurry. You've got too much moisture in it. Fly ash modification of a lot. We had a lot out here in northwest Houston, and the subgrade was pumping. You didn't pass proof rolling. So the owner was saying, hey, you got to pass proof roll. Is it pumping here? You can't build a house on it. So there was sandy soils. You can see all the sand. You got fly ash, dump it over here. They went out there and started mixing it in. Add water to it. This is a sand fly ash mixture. Start adding water. Compacted between 2 to 6 hours. Compacted it with a steel drum roller. That's what it looked like after it was compacted. It was 12 inches thick. Cast proof roll. Uh-oh. And you check with density. Make sure you pass compaction. And we checked the depth of fly ash with phenol failing. Turns purple all the way down for 12 inches with fly ash. So that was effective. It passed proof rolling. You can always remove and replace the sandy soils and silts with good structural fill, a clay type material. You dig out the sandy stuff, haul it off. You bring in structural fill, compact it with sheep's foot. Disking, where you're doing earthwork on a lot or on a subdivision or the subdivision, you cannot compact big chunks of clay. So you get that chunks of clay, you get a disc machine, and you disc it to small pieces of less than 1.5 inches in size. Chop it to small pieces. Proof roll before you build your house. You got to proof roll that pad. But natural soil, actually. Natural soil before you put any fill in it. You proof roll it. Make sure there's no deflections. You get a loaded dump truck, somewhere between 25 to 50 ton. This is not acceptable. 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 So you got to pass proof rolling before you put your slab on there, especially some of these post-tension slabs. If you put them on the soil that's not properly compacted, you're going to have all kinds of foundation problems. Earthwork for a single lot. You dig out the sandy soils here. You got a perch water table. You take out all the sandy soils. You stockpile them. You get to the nice hard clay. Here's all the sand that was removed. You proof roll it. You bring in select structural fill. Well, structural fill doesn't have to be select. And start compacting it, run density tests, make sure it passes density. Compaction, if your soils are clayey, you would use a sheep's foot roller. If your soil's sandy, use a steel drum roller. Okay, steel drum roller vibrates the sandy soils, compacts them better. Sheep's foot is good for clay. Use dozer for grading purposes. You don't use dozer for compaction. It doesn't have much weight to it. It's not designed for compaction. Do not use dozer for compaction. And then you seal with a pneumatic roller. You seal your pad, your roadway. You fill this up with water. You go back and forth. You compact with a sheep's foot and you seal it with a pneumatic. If this is your pad in here, you compact with a sheep's foot. Then you come back with a steel drum roller and you seal it. So when it rains, water doesn't penetrate your pad. This is a pad that's not graded properly. You can see water standing. This is one of our technicians, Mr. Patch, standing over there looking at it. You got all this bird bath that messes up the pad. All this needs to be digging out. You have to dig it out, dry it up, put it back in again. So that's not acceptable. Let's see. Seems like just checking to see if there's any questions in here. I don't see any questions in here. Okay. House path construction. If you got side is wooded, you got to get out there and take out those trees. All the roots greater than 1/2 inch to come out. Remove all that grass. You got to take out top 6 inches. Start bringing fill. Who's a structural fill? You bring it in. If it rains and you got bad drainage, you got that bird bath. You got to pump that water out. Pump it off site. You got to go back and proof roll it again. Proof roll it. It sink, reject it. You got to dig it out and dry it up, put it back in again. Not acceptable. Then you bring the select fill after you pass proof roll. Put structural fill. Start spreading it out. Compacting with the sheep's foot. Build your pad. Start putting this in your forms. Put in your plumbing. Tear up the whole slab when they put the tear up the whole pad when they put the plumbing in. You got to go back and compact. Put your vapor barrier in. Put post tension cables in. You pour your concrete. PVR for post tension slab should be less than 4.5 inches. If you buy lots with PVR greater than 4.5, you got to do chemical injection or moisture conditioning. There's a subdivision out there in Sierra Vista subdivision, Brazoria County. PVR 4.9, 4.9, 5.2, 5.1. You got to test every lot. 5.1. You got to keep that PVR to less than 4.5. So you do a chemical injection. You either put select fill on the lots to get the PVR less than 4.5. You can do moisture conditioning or chemical injection. We talked about chemical injection. You can put select fill on the lots, but it changes your elevation on your lots. So it's not a very practical way to reduce your PVR if you put select fill in, unless you take out top few feet and put select fill in. So that's not very practical. That's a select fill with a soil with liquid limit less than 40 PI between 12 and 20. You can do moisture conditioning. You got to get in there, take top 2-3 feet of that site. You remove it, you add water to it, you make it wet and compact it on the wet side of the soil, on the proctor side, optimum plus 4%. It's called moisture conditioning. Compact it with a sheep's foot. You compact it at optimum plus 4% of the proctor test. Packed it. After moisture conditioning, you got to compact that soil 95% at optimum plus 4%. You got to extend 5 feet past the floor slab footprint. You got to cover it with moisture like a visqueen within 14 days. Otherwise, it will lose the moisture, especially during the drought summertime that we got. And then you put 12 inches of structural fill on top of that, and then build your slab on top of it at a future time. So that's called moisture conditioning. That gets your PVR to less than 4.5. So if you got a proctor curve on your fill, you compact that soil at optimum plus 4%. If your optimum is 11, you compact it at 15% and 95% standard proctor density. Okay. Conduct post moisture conditioning swell test to make sure in the moisture conditioning was effective. So you got to go drill holes out there after you moisture conditioned, run swell tests to make sure your PVR are less than 4.5 inches. Cover the area that has been moisture conditioned with plastic sheeting as soon as possible. After you compact at optimum plus 4%, you cover the area with plastic sheeting like that. Your moisture kind of cover it. You got to cover within 14 days. We talked about chemical injection as an option if your soils have got a high PVR greater than 4.5. And if you do chemical injection, you got to do post-injection testing. You drill holes to a depth of 10 feet. You run swell tests, make sure your PVR is less than 4.5. Lot drainage, when you build lots, build houses, your lots got to have positive drainage. Usually you want to have 5% slope on your lots. Get that water away. If you got a pad, you got to have positive drainage. These are the houses that built, post-tension slab. You got positive drainage towards the street. Sometimes they put swales between the houses to get that water from the backyard away into the street, the storm sewer. Here's the swale. In terms of testing, when you do a house construction, you got to do test swalls, concrete, piers. This is the pad out there. They're going to do post-tension slabs out of here. Pad 3 to 4 foot thick. They got to bring in fill. So they got to bring in select fill. This is the natural soil. This is Kingwood, highly expansive soils. They bring in select fill from a pit. You get 50 pounds of that material. You run a proctor test on it. Then you go out there and get your fill material from a pit. Pit is a big hole in the ground. It's got different soils. This area is sandy. This area is sandy clay. So depending which part of the pit you get your material, you're going to have different type of soils. You get a backhoe, you get your trucks out there, line them up. You get this select fill. You put them in the back of the truck, or you put them on a hopper. You fill up the trucks. That's your select fill. That's your natural soil. You bring the soil, you dry it up, chop it to pieces. You add water to it at the various moisture conditions. You compact it for standard proctor. You got 5.5 pound hammer, drop 12 inches. This is a 4-inch mold, 25 blows per lift, 3 lifts. 5.5 pound hammer, 12 inches, 25 blows per lift, 3 lifts. You compact that soil. Machine does it for you. Compact it. This is the mold. You know the volume. You extrude the sample. You weigh it. You know the volume. You know the weight. You get the density. At soils at different moisture, you develop different densities. If your soil is too dry, you got low density. If your soil is too wet, you got low density. You develop an optimal moisture, you develop the maximum density and maximum strength. So here's 11% at 120. You compact that soil for your pad, 95% of standard proctor density. So that's 115 pounds per cubic foot. At moisture content plus or minus 2% optimum, all the way from 9 to 13%. As if you run your proctor in here, you can see the strength test on that soil. You develop the maximum strength near the optimum. If you got a small area, you use the jump and jack to compact the area. Small lifts, or use a small sheep's foot or steel drum roller to compact your pad. The area needs to be clean. Do not use sand in your forms. Sands are permeable. Water gets all over the place. If the water gets in there from a plumbing leak, bad drainage, you develop perched water table under your slab. That's not good. Water comes through your slab and your tile's going to come off. So when you build your pad with structural fill, sandy clay, silty clay, positive drainage, set the forms in, your plumbing, you got to go behind the plumbing after they put them in and compact that soil because the plumbers will screw up your slab. You compact, good grade beams, no loose materials. All these loose materials need to come out. Run density tests for your pad. You got to run density tests for every lift, every 8 inches. You got to run a density test per lift. You poke a hole in the ground, put your nuclear gauge in there. This is your nuclear source. You put the rod in there. It emits gamma rays. You got detectors in here. The more it comes over here, the looser your soils are. The less it comes over here, you got the denser your soils are. It takes about 30 seconds. On a single custom home, we would typically run 5 density tests per lift. For a production builder houses, 1 density per lot per lift. Here's the density, you measure it. Your proctor test. Optimum is 11, optimum plus and minus 2%, 9 to 13%, 115, 95% standard proctor density. You dig your grade beams. This is not acceptable. This is not acceptable. All the trash needs to come out. Bottom of the grade beam should be nice and hard. This is not acceptable. This is a custom home. They're digging out the beams and dump it on the pad. Got all that fat clays in there. It's not good. That busted the steel on your piers. Bad construction. You're going to use a lot of concrete because your beams are not cut properly. So bad construction here. Beams are not vertical, clean. All the loose material on the pad needs to come off. You scrape off all the loose stuff. You put your vapor barrier in. This is a pad after a rainfall. It's not acceptable. Here's a pad that left the trees in there next to him or inside the pad. 26-inch tree trunk stump in the beam. Here's a 14-inch pecan, 37 inches from the form, not acceptable. 26-inch stump right here in the slab. 6 to 8 inch slump in the beam. All that stuff needs to come out. You can't have trees near the foundation within 20 feet of the slab. All the roots greater than half an inch got to come out. And everything got to be compacted 95% standard proctor density every 8-inch lifts. Here these guys are building the pad. They put little forms around them. Nice, clean job. This is another slab here. It was raining all the time, so they put a tent on it. They dug the beams, and here's that's the church project out there next to the GHBA building, out there on Beltway 8 near West Road. They set the forms, grass grew on it, and they poured concrete. It's not acceptable. You can't build a slab like this. All the organic needs to come out before you pour concrete. If you leave something open like this for a long time, you got to go back and proof roll it, compact it, pass it, and do it again. That's the church that sits on that property right now. Remove the grass and weeds before you set the forms. This is one of the subdivision in North Houston. These guys go out there and they didn't remove the grass. They didn't do any proof rolling or nothing. They just go out there and set the forms and pour the concrete on top of the grass. Dug their beams. This is their post-tension slab. That's the grass. That's the grass. So they got grass at their beams. Real bad construction. Correct fill type. We don't use sand in your forms. Don't use sand. Use a structural fill. All around plumbing, use a structural fill. Don't use sand. Sand causes perch water table. If you're building up your pad out there on a subdivision lot, all this pad got to be compacted in 8-inch lifts. You can't just set the forms and fill them up with soil and put a slab on top of it. Not acceptable. Got to be structural fill. You can't have these chunks of clay in there. It's not acceptable. So when you fill up your forms out there, and this is your fill, and we check them, it's all fat clay in there with sand around it. That's not structural fill. That's fat clay. Grading plan. We see all these subdivisions out there in North Harris County and Montgomery County. And they got a lot of topography to them. So you got grading. Their lots. So you got a lot of cut and fill. And you got to check the compaction of this fill because of the cut and fill. You do mass grading. So you're buying lots out there, there's a lot of fill on them. And you got to make sure this fill is properly compacted. If you don't have any densities when you buy lots, or you don't have enough densities, only you have only densities for the top 8 inches, that's not acceptable. A 79G letter of top 8 inches is not acceptable. If you have fill, we got to go in there and check your lots. Let's say your lots are the red ones. You got to do 1 boring every lot if your soils are clay. So if you got clay soils, we go out there, drill holes, and get samples of the soil. We run density tests. Make sure every 8 inches is properly compacted. Then we say that's good. If your soils are sandy lot, then we got to go out there. We cannot get clay sample. You go out there and run density tests with a backhoe. You run one on the surface. You start digging holes. Put the gauge in there. Every 8 inch, you go down and run density tests. You got to do 1 per lot. Make sure all your lots properly compacted. Concrete testing. You cannot pour concrete on your slabs if temperature drops below 40 degrees. You can pour concrete if the temperature is at least 50 degrees and for at least half a day. If your concrete is you're pouring in a condition, temperature is freezing, and you got low temperature below 40 degrees, you get low strengths. Low strength gain with time. More void space in your concrete corresponding to low strength. The reduced rate of cement hydration corresponding to low strength, lower durability. You got to make sure your concrete at least get 500%, 500 psi when you pour it if the temperature is freezing. You can put blankets in, heaters. You got to get to at least 500 psi. Protect that concrete. Once you get to 500 psi, you can have 1 cycle of freezing and your concrete is still going to be good. The 500 psi usually achieved within 24 to 48 hours. If the temperature is hot, when you pour your concrete should be between 75 to 100 degrees. Make sure you check the temperature of the concrete. If the weather is really hot when you pour concrete, it's going to require increased water demand, actually the slump loss, increased rate of setting, increased tendency for plastic cracking, difficulties in controlling entrained air, critical prompt early curing, decreased strength, decreased durability, non-uniform surface appearance, increased tendency for drying shrinkage. You got to take care of these things when you pour concrete. New concrete after rain, these guys out there pour concrete, then it rained. You washed out all the cement off the aggregates. You can see the steel. So now to jackhammer that up and put it again. When you pour concrete, you pump it in. The slump should not be more than 5 inches. You got to start finishing it. Make sure you got chairs underneath your steel. If your slab is big, you suck out 4 to 12 hours after pour. That's a conventional reinforced slab. You suck out 1/4 of the slab thickness to tell it where to crack. You don't do this if you got post-tension slab. That's for a conventional reinforced slab. You saw cut. If your slab is 4 inches, you saw cut 1 inch. You saw cut 1/4 of the slab thickness. The slab will crack underneath it. You got it at 4 to 12 inches, 12 hours after the pour. You run slump tests to make sure your slump is less than 5 inches. The way you run it, you put concrete in this cone, 3 layers, 25 blows per layers. You compact that concrete, make sure there's no voids. After 3 layers, you pull it. You measure the slump from here to here. That should not exceed 5 inches. This is 11 inches. It's got too much water in the concrete. You reject that concrete. Yours is too stiff, 1 inch slump. You reject that concrete. 5, add 5 gallons of water to your concrete. That's bad news. You don't add water to your concrete at the job site. Adding 1 gallon of water to 1 yard of the concrete increases the slump by 1 inch. 1 gallon of water to 1 yard of concrete would reduces the strength by 250 psi. 1 gallon of water wastes 25 pounds of cement. 1 gallon of water increases shrinkage by 10%. 1 gallon of water increases permeability by 50%. 1 gallon of water reduces the freeze-thaw resistance by 20%. 1 gallon of water reduces salt scaling resistance. 1 gallon of water increases cracking by 10%. Increases air content by 1%. Increases segregation. All the big stuff comes on the bottom. You get soup on the top. So you're going to get really a bad concrete. You get low durability near the top. A lot of flaking. Increased water damage from traffic. Increased dusting. Increases the finishing time. Is 1 gallon of water worth it? No. Here's these guys add a bunch of water to the concrete for the slab. This guy uses a key and just, you see the slab, the concrete is coming off. So they have to jackhammer that concrete and pour a new slab. Here's another slab here. They poured it. They didn't vibrate it. Here's the concrete. That's what it looks like. Too much water. Record it. Bad concrete finish. The pours. We ran the tests. Okay, at 1 day, they had 710. At 5 days, 800 psi, 1500 psi, 1100. They had to go in there and remove the whole concrete and put a new slab in. That was bad concrete. Making cylinders. When you pour your concrete, you make cylinders on the job site. These are 6 by 12 inch cylinders. You put concrete in 3 layers. You rot it in 25 times per layer. Compact that soil, that concrete, make sure there's no voids. Clean the top. Cap on it, leave it on the job site 24 to 48 hours. You put it in this concrete cylinder holders. You take it to the office. You put it in a curing room. Keep it in 100% humidity, 72 degrees. You break it. If it's a 3,000 psi concrete, you should be at 3,000 psi at 28 days, 2,100 psi at 7 days. If your concrete is bad, you core it. You core the concrete. You cap it, put it in a machine, you break it. In general, concrete core results are 15% lower than cylinders because of the curing. The curing on the job site curing is not as good as curing 100% humidity and constant temperature. So the strengths can be usually 15% lower. If your concrete's got low strength, you check it with Swiss hammer. That's Swiss hammer right here. It's got a spring-loaded piston in here. You scrape the ground with this, make it flat. You push it in. You let it go. You can read here on the spring what kind of a strength it has. Usually overestimates concrete strength. You can use Windsor probe. It's a gun with a bullet in it. You shoot it into the concrete. You set it up on the concrete slab. This is your bullet. You shoot it in. This is what you get based on the size of the aggregates, the size of the hole and the depth. You measure, it tells you what the concrete strength is. These are considered non-destructive testing. Drill piers. We talked about drill piers before. You got a custom home, you put them on piers. It's auger rig, bell. Drill your piers. This is a auger rig there. Drill the holes. That's a reamer. 36 inches typically for residential. Make sure it opens up. You got to measure it. It's measured 36 inches. You can have up to 3 inches of water. You put, make sure you got a proper depth. You check the soil at the bottom. Make sure it's got proper strength so that you have proper bearing capacity. Make sure the hole is vertical. Bell tool, you run it in there. Make sure you got right size bell. Put your steel cage in. For the concrete, make sure it doesn't hit the sides. Drill a hole with the auger. You put your steel cage in. You pour concrete. That's a dry method of construction. Now, if you got sandy soils and you got caving problems, use casing method of construction. You drill a pilot hole. You put your steel casing in it. You drill inside the casing. Take the soil out. You check for hand penetrometer. Make sure you got a proper strength. You put the bell tool in it. Make your bell. Put your steel in it. You start pouring concrete. You pull out your casing. You're trimming the concrete from top to bottom. It's like a funnel. Pour the concrete down so that you don't get segregation. A lot of the jobs, we got sandy soils and shallow water table, you got to use a slurry method of construction. The cost of slurry method of construction is 3 times than dry method of construction. This is where you would be using helical piles. So you got a mud pit with bentonite in it. It's a mud pit. You drill the hole. Start mixing the bentonite with water. You put your cage in. You start pumping the concrete. You put a hose. You start putting the concrete from bottom up. That replaces the mud. You put the hose in all the way in the bottom. Pump the concrete in. The mud, of course, that you introduce, the bentonite, it seals the sandy soils and develop a cake in here, bentonite filter cake. Plus the hydrostatic pressure from the mud keeps it from collapsing. So in a slurry method of construction, you drill a hole, you add a slurry to it, you keep the hole open, you put in your cage, you're starting to trim the concrete from bottom up. You recycle the bentonite, the drilling mud. You recycle it for the next one. So that's the end of my presentation. If you got pictures of the projects, especially like failures or construction, slurry method of construction, good pictures of residential construction and design, send them to me. Appreciate that. You can go to YouTube and see this presentation again. There's a lot of information. Program evaluation. You got to look at this thing here, and it's supposed to be a pole in here. I don't see it. Let's see. Yeah, I don't see a pole here. Let me check if I have. Let's see, there's a poll here. It's loading it right now. Yeah, please respond to the poll. Tell us what you think of the presentation. If you need to reach me, my email is de@geotecheng.com. My phone number is 713-699-4000. We're going to have a bunch of upcoming webinars if you're on our database to get notices of them. Questions? A lot of materials. Any questions? Any questions, comments, anything? Question here for select structural fill. What do you recommend as minimum passage through number 200 SIF? 50% should pass. Is fly ash or cement stabilization applicable only to sandy soils? No, you can use them for fat clay too. But typically for fat clay, you use quick lime. That's a lot better if you want to dry them up, and if you want to stabilize them, you use lime slurry. Anything else? Great presentation. Howdy, I enjoyed your seminar. Will you send me evaluation via email, okay? Great presentation. Any questions? Well, there's not that many questions, so I appreciate y'all time. I guess we'll see you in the next webinar. Y'all have a great day. Thank you.